Hi, in this example, we're going to use the central limit theorem to solve the following problem. Let x be a random variable. Suppose that x has a normal distribution with mean 54 and standard deviation 6. Suppose that random samples of size 10 are drawn from the data and x bar represents the sample mean. Part A. What is the mean of the sampling distribution? Part B, what is the standard deviation of the sampling distribution? Part C, what's the probability that the mean x bar of 10 data values taken at random is less than 49? Part C, what is the probability that the mean x bar of 10 data values taken at random is less than 49? Part D, what is the probability that the mean x bar of 10 data values taken at random is between 49 and 60? And finally, part E, what is the probability that the mean x bar of 10 data values taken at random is greater than 57? So since the distribution of the values of x is normal, with mean of 54 and standard deviation 6, by the central limit theorem, we also have that the sampling distribution of x bar made up of samples of size n, so little n is 10, this sampling distribution is also normal. So for part A, we're going to determine what is the mean of the sampling distribution. So the mean of the sampling distribution by properties of the sampling distribution is the same as the underlying population. So we have that the mean of the sampling distribution is 54. So part B, we're going to determine what is the standard deviation of the sampling distribution. The standard deviation of the sampling distribution is the population standard deviation divided by the square root of the sample size. So the mean of the sampling distribution is 6, the standard deviation of the underlying population, and we're going to divide this by the square root of the sample size, which is 10. Doing this computation, we have that is approximately 1.9 rounded off to one decimal place. So now let's take a look at part C. What is the probability that the mean x bar of 10 data values taken at random is less than 49? So we know from part A and B, an application of the central limit theorem, that the sampling distribution, the x bar values, has a normal distribution, and we also determined that the mean of the sampling distribution is 54 with a standard deviation of 1.9. So for part C, we wanted to compute the probability that if drawing a random sample of size 10, the sample has a mean that is less than 49. In order to compute this probability, we know that we are working with x bar distribution, which is normal. What we're going to do, we're going to convert the values, the scores, to the standard normal distribution. Therefore, we want to compute this probability, which is the same as the probability that converting the x bar values to z values, the standard normal distribution, we have that the z value is less than the z value of 49. Now, the z value of 49 is 49 minus the mean, which is 54, divided by the standard deviation of the sampling distribution, which is 1.9. Common mistake is that when students convert the value to a z-score, common mistake is when students convert the normal distribution to the standard normal distribution, they use the original standard deviation from the population and not the standard deviation of the sampling mean. So please notice that we actually divide this by 1.9, which is the standard deviation of the sampling distribution, and not divided by 6, which is the standard deviation of the population. We are working with the means of samples, X bar. So we have that the probability we're looking for is the same as the probability that the z-score is less than negative 2.63 when we round it off the z-value to the second decimal place. The probability of the standard normal distribution corresponds to this area, and this is the area to the left of the z-score of negative 2.63. To find what is the area on the left side of z-score negative 2.63 under the standard normal curve, we're going to look up this value in the table. So the table shows us that the left area of z value negative 2.63 corresponds to the value of 0.0043. So since the area corresponds to the probability we're looking for in the standard normal distribution, which is equivalent to the probability in the original normal distribution. Part D. What is the probability that the mean X bar of 10 data values taken at random is between 49 and 60? Symbolically speaking, this is the probability that X bar is between the values of 49 and 60. So we want to find the probability that at random we pick a sample that yield a mean that is between 49 and 60. Again, to compute this probability, we're going to convert the X bar value to Z values, meaning we're going to work with the standard normal distribution. So the probability that X bar is between 49 and 60 is the same as the probability that when we convert this value to z-score, the z-score is also going to be between the z value of 49, which is 49 minus 54, divided by the standard deviation of the sampling distribution, which is 1.9. Whatever that value is going to be less than the z, which is less than now the z-score of 60. So z-score of 60 is 60 minus 54 divided by 1.9. So the computation yield that the z value of 49 is negative 2.63, which is less than z, which is less than, now the z-score for 60 is 3.16. So this probability corresponds to an area under the standard normal curve between the z values of negative 2.63 and positive 316. And the area between two z-scores is the area of the largest z-score, which is 3.16, the area to the left of that, minus the area to the left of the small z-score, which is negative 2.63. So looking up these values in the standard normal distribution table, we have that the area to the left of 316 is equivalent to 0.9992. And we're going to subtract from that the area to the left of negative 2.63, and that corresponds to 0.0043. So the result is 0.9949. Okay, now part E. What is the probability that the mean X bar of 10 data values taken at random is greater than 57? We have that to compute the probability that X bar is greater than 57. And again, to compute this probability, we're going to rely in the computations under the standard normal distribution. So first we're going to convert the values, X bar values, to z-scores. So this probability is equivalent to the probability that the z value, when I convert X bar to z-score, is greater than the z value for 57. And the z value for 57 is 57 minus 54, which is the mean of the distribution X bar, divided by the standard deviation of the X bar distribution, which is 1.9. So the probability that the z value is being greater than 1.58 is equivalent to the probability that the mean x bar of 10 data values is greater than 57. Now, we know that this corresponds to a right side area, so this probability is the same as the area on the right side of the z-score of 1.58. And to compute right side areas, we compute actually the subtraction of the total area under the standard normal distribution. The total area is 1 minus the area to the left of the z-score of 1.58. So our probability is equals to 1, the total area under the standard normal curve, minus the area to the left of 1.58 that corresponds to the value of 0.9429. So the value we're looking for is 0.05721. Therefore, the probability that x bar value is greater than 57 is equals to 0.571.